Hello everyone, this is Varun from VIT University Chennai. This session we will be dealing on columns, that is we will be mainly concentrating on introduction to columns and design of short columns. Before moving into the column system, we'll see what a compression member is. We all know that column is an example of a compression member. When we concentrate on the definition of the compression member, it can be defined as a structural element which is primarily subjected to axial compressive forces. The main examples for compression members are pedestal, column, wall, and strut. Pedestal, columns, and walls carries the load along its length in the vertical direction, while the strut in the truss carries the load in any direction. Let's see what a column is as per IS 456 2000. The clause This definition is as per the clause 25.3 of the IS 456. Column is a vertical compression member whose unsupported length L shall not exceed 60 times of B, that is the least lateral dimension, if restrained at 2 ends. Further, its unsupported length of a cantilever column shall not exceed 100 B squared by B, where B is larger lateral dimension, which is also restricted up to 4 times of B. Classification of columns. Column can be classified on the basis of its cross-section, then the type of reinforcement provided, and the basis of loading, and bond based on the slenderness ratio too. Let's see the different types of columns based on the cross-section. This is mainly for the architectural purposes, that is column is classified as rectangular, circular, square, hexagonal, plus C-shape and L-shape. When we consider the type of reinforcement provided, it is classified as side column, spiral column, and composite column. Based on the type of loading, the column is classified as concentrically applied load, with columns with uniaxial eccentricity and columns with biaxial eccentricity. Here, this first picture, that is the axial compression. This is the axial compression, that is a force P is applied on the center of gravity of the column, where in the second case, that is this case, the force or load P is applied at a distance from the center of gravity, and there is an eccentricity E here. And while that this is the uniaxial bending case, while this case, that is load is applied at an eccentricity Ex, and also it is having an eccentricity of Ey. Next is the classification of column based on the slenderness ratio. Hope you all know what is slenderness ratio. It is the ratio of effective length LC to its least lateral dimension. Effective length is very much different from unsupported length. There is a relation between the LE and unsupported length. That is, effective length can be found out by K into L. That K value can be different for different cases, that will be seen in the next slide. For a rectangular reinforcement concrete column of cross-sectional dimensions B and D shall have two effective lengths in the two directions. That is, accordingly, this can have the possibility of buckling depending on the two values of slenderness ratio. That is, we will be having a slenderness ratio about the major axis as well as it will be having a slenderness ratio about the minor axis. Along the major axis, it will be Lex by D, while along the minor axis, it can be Ley by B. We told that there is a relation between the slenderness, that is effective length, as well as the unsupported length, that is Le is equal to KL. These are the different conditions of the column, that is both ends restrained, and we have, and for that the recommended factor is written here. This is the table 28 of IS 456, which you can refer to. The classification of column based on the above discussion that we discussed so far can be classified as short column as well as long column. Let's see what a short column is. When the slenderness ratio, that is Lex by B and Le by B, both are less than 12, then we can consider it as short column. As said, Lex is the effective length with respect to major axis, and Ley is effective length in respect to the minor axis, and the d is the depth in respect of the major axis. D is the width of the member. If any one of these ratios are greater than 12, any one is greater than 12, then we can conclude it as a long column. Now let us see a simple problem on a short axially loaded column. Here in this problem, we have to design a rectangular column which is subjected to a load of 3030 kN under dead load and live load P. The column is having brace against side sway in both directions and is having unsupported length of 3.20 meter, and consider M25 concrete as well as Fe415 steel, and assume a moderate environment. Now, for the first step of the design of the column, we have to determine the size of the column. In order to determine the size of the column, we will assume a factored load. We find out the factored load. Factored load is just 1.5 into the axial load. The axial load is 3030. That is 1.5 into 3030 will give you 4545 kilonewton. Assume let us assume the percentage of steel here as 3%. So from that we can find out the value of AC, that is the cross-sectional area of the column. AC can be found out by this equation, substituting the value of PU and FCC, FY and the percentage of the steel. In this particular equation, we will get the cross-section of the column, that is 248136 mm square, and we will assume it as 450 mm by 600 mm size of the column. When we multiply this 450 by into 600, we will get this value. So the provided value, the provided area of cross section is 270,000 mm square. Next, let us see whether we know if, though we know we are designing a short column, we will see whether we will check whether it is correct or not. For that particular condition, that is base condition, effective length factor is 1, K value is 1, that is Le is equal to KL relation we already told. And for that, from the table 20 of IS 456, we will get K as 1. See, according to clause 25.1.2 of IS 456, the compression member can be considered short when both the slenderness ratios, that is Lex by D and Le by B, is less than 12. We are taking both the conditions at 3.20 divided by 0.45 is 7.11, and the other condition is 3.20 by 0.5 is less than, it gives 0.45 gives also less, 0.5 gives also less than 12, hence we will conclude it as a short column. Then we will check for the minimum eccentricity that is happening in the column. The minimum to there is a close, it is be as per the close I is 25.4. That is close I 25.4 states that all columns shall be designed for a minimum eccentricity which is equal to unsupported length of the column by 500 plus lateral dimension by 30, subject to a minimum of 20 mm. Where biaxial bending is considered, it is sufficient to ensure that eccentricity exceeds the minimum about one axis at a time. So we will find a EY minimum. EY minimum should be the greater value of LEY by 500 plus D by 30, and we will get it as 21.4. So the greater value of 21.4 and 20 mm we will choose as the EY minimum. And similarly, we are finding out EX minimum. That is we will find out the value of LEX by 500 plus E by 30 and 20. Whichever is the greater among these two, we will take it as the EX minimum. That is, we will get, and while doing this particular, solving this particular equation, we are getting it as 26.4 mm. Also, we are finding out the eccentricity at is 0.05 into B, that will be giving us 30 mm, and the 0.05 B will get just 22.5. Hence, it's applicable for the design here. Next, we are going to estimate the longitudinal reinforcement, that is for this equation. The only unknown is ASC in this, and from here we get the 6635 mm square. And as per clause 26.3.1, the cross-sectional area of a longitudinal reinforcement shall not be less than 0.8% or no more than 6% of the gross cross-sectional area. Even we see that much is it should not be more than 6%. For the practical purposes we restrict up to 4% only. So we are finding out the minimum reinforcement, that is 0.008, that is 8.8% of the gross sectional area. We'll get it as 2160 mm square, which is less than what? It is less than 5535 mm square. So here we provide 620, 28, 28 mm bars and 432 mm bars. So the provided value, that is provided reinforcement, will be 6911 mm square. So we'll check what is its percentage, and that is the 2.56%, which is less than 4, which is less than 4%. So it is within the limit, so can be designed. Now next is estimating the transverse reinforcement. In case of the transverse reinforcement, we have to consider the clause 26.5.3.2, that this clause states that the pitch of the transverse reinforcement shall not be more than the least of the following distances. Three cases are there. The three cases are the least, that is, these three cases are the least lateral dimension of the compression member, 16 times the smallest diameter of the longitudinal reinforcement has bar to be tied, and 300 mm. We find the three values, and whichever is minimum, we'll choose that. Here the smallest of the 450 mm, and 16 into 25 mm, that's 400 mm, and the 300 mm. We'll get it as 300 mm is the lowest value, so we'll choose that as it is. Also find the diameter. The diameter of the polygonal links or lateral ties shall not be less than 1/4 of the diameter of the largest longitudinal bar, and in no case it should be less than 6 mm. So here we can see that the diameter of the largest bar is 32 mm. So diameter of the lateral tie will be 8 mm. This is the detailing that is given, that is all at the corners we had provided 32 mm bars, and all others are 25 mm bars. So this we conclude this problem. We will go into another problem in which we will be dealing on the biaxial bending is there biaxially loaded column. And the problem is the design a biaxially loaded braced circular column for the following data, that is bracket load being as u equal to 1875, ultimate biaxial moment MUX and MUY are given. MUX is equal to 190 kilonewton meter and MUY is equal to 100 kilonewton meter. The unsupported length is equal to 3.25 meter. The diameter of the column is equal to 500 mm and we are using M25 concrete and 415 grade steel as a moderate environment. We are given two moments, that is MUX and MUY in the question. So first of all, what we have to do is the determination of the equivalent uniaxial moment. We will determine the equivalent uniaxial moment by this equation, that is Mu is equal to the square root of MUX square plus MUY square. From that we will get the equivalent uniaxial moment at 214.71 kilonewton meter. Next is the check for moment due to minimum eccentricity. That is we are taking the equation already mentioned in the last problem. With that we will get just 23.1 mm. And from that we will getting all the moment which is less than the applied moment. Moment is equal to 43.4 kilonewton meter. And next is the determination of the steel reinforcement, and this is done using ST16. And so we will find that 40 mm cover we are taken, so we will find the D dash value. D dash value is obtained by 40 plus 8 plus 25 by 2. 40 is the cover that is mentioned in the question, then 8 is we are providing 8 mm ties and we are using 25 mm longitudinal bars, that is the 25 by 2, and thus we obtain the value 60.5 mm. Then we have to find the D dash by D ratio. D dash by D ratio is obtained at 0.121. The D dash by D ratio is required as it is referring to ST16. And when we refer ST16 and we have to find these values of these two equations, that is Cu by FCK d square and Cu by Mu by FCK d cube. When we find that, we will get the Cu by FCK d square as 0.3 and Mu by FCK d cube as 0.0687. Then refer the chart 57 from where we get the percentage of the C. Actually, we will not directly getting, we will be getting C by FCK value getting from the chart 57. If we get C by FCK, we know that we use M25 grade concrete, we will get the value of C at least the 2.5 percentage, which is less than 4 percent, hence it is within limit. So we will find the area of the steel. 2.5 percentage into the area of the concrete will get the area of the steel, that is 4908 mm square, 4908.7 mm square. It's providing 1025 mm bars, thus we are obtaining this value as 4 provided value as 4908 mm square. Now again we have to find the diameter of the transverse reinforcement. Those things we have to find. Diameter is equal to greater of the 25 by 4 and 6 mm. The diameter is equal to 6.25 mm. We got using 8 mm bars instead. The pitch 500. The value is the least 500 is the dimension of the diameter of the circular column, and then the 16 times the diameter of the uh, longitudinal reinforcement used, and the third condition is the 300. Minimum of these values are preferred, and we will prefer it as 300 cm distance as it is the minimum. So the detailing, that is we are providing the 8 mm lateral ties and 10-25 mm bars in the 500 mm diameter column. With this we conclude the session on the short column.